Hello, good people. We're now embarking on 4.7, coordinates and change of basis. So, what are coordinates? You have like a point on the plane, so it's x comma y. So 2 comma 3, 2 is the x coordinate and 3 is the y coordinate, or so on and so forth. Well, a coordinate just means uh, a coordinate such as 2 comma 3 just means 2 times a 1-inch horizontal vector, which would be would be the vector 1 comma 0, plus 3 times the vertical vector, 0 comma 1. And any point in the plane can be represented as a coordinate, because you ready for this? Drum roll, please. Because the vector 1 0 and the vector 0 1 forms a basis for R2, so therefore you could take linear, any coordinate point is really just a linear combination of those two vectors. Well, who says that we have to pick those two vectors when we do coordinates and we want to find points on the plane? What if we pick any other two vectors that would form some kind of a basis? Well, that is what we're talking about: coordinate representation in Rn. And normally, you know, we're used to just writing, 2 comma 3 or something like that. But what if we use a different basis? Then we talk about the coordinates of x, coordinates of a point x or a vector x, relative to a basis b. So here's the official formal definition: that if b is a bunch of n vectors, which is an ordered basis. Now, ordered. First of all, what does an ordered basis mean? Really, when you have a set like this of bases of vectors, the order of the set never made any difference. And it's not like it makes damage of a difference now. The only thing is I want to be consistent. I want to know that constant 1 goes with vector 1 and constant 2 goes with vector 2. I kind of want to, just like when you have a point in the plane, we call it an ordered pair, because you want to make sure the x is first and y is second. The same thing here, just to keep things, in order in the court. Anyway, x is a vector, where x is equal to x is some random vector, and x equals c1 v1, c2 v2, dot 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 up to cn vn. And I know that any vector x I can express this way because the b is a basis. Anyways, the scalars c1 comma c2 comma cn in that order are called the coordinates of x relative to the basis b. And there's something that we call the coordinate matrix, which is just a coordinate vector of x relative to b, is the column matrix whose components are the coordinates of x. So c1, c2 down the line all the way to cn. And notice that I write a little x thingy here, and I put a little b there. And the reason I have to put that little b over there is because otherwise, if I just wrote, if I didn't have the b, I would think that this is the standard. I would confuse this with the standard, quote, the standard basis. In other words, 1 comma 0, 0 comma 1, that's the standard basis. Anyways, let's move on. So in Rn, the coordinate notation is just x1 comma x2 dot dot comma xn, and this is relative to the standard basis s. So xs is this guy right there. Now, normally we don't bother writing the s because that's the standard basis. Just like when something is log base 10, you don't write log base 10 because that's the common logarithm. Or square root, you don't write the little 2. Cube root, you write the little 3 up in the upper left corner. But in square roots, you don't bother writing it because it's so common. Anyways, let's do an example. Suppose we have the point -2, comma 1, comma 3 in R3, and we want to write that relative to the standard basis. Well, no big shock. That's just going to be xs is going to be -2, 1, 3. And again, that was pretty much of a slam dunk. But why has it worked? Now, of course, that was simple, but I really just want to make a point here. Why did this work? Because x is equal to x, which is equal to -2, 1, 3, is -2 times the first vector plus +1 times the second vector plus 3 times the third vector. By the way, sometimes, very often, especially if any of you guys took like Calc 3, this vector here is often referred to as the I vector. That's often referred to as the J vector, and that's often referred to as the K vector. You know, if it was if it was in 2 dimensions, then the 1, 0 would be the I vector, 0, 1 would be the J vector. It's just a common usage, I and J. But anyway, that's really what's going on here. That's what it means. -2, 1, 3, and that's how you express it as a vector or as a linear combination of these basis vectors. Now let's do one where it's not the basis, where it's not the standard basis. I mean, let's look at we want to find the coordinates of x, and we're in R2, and we want to find the coordinates of a point relative, the coordinate matrices, they have a point relative to the non-standard ordered basis v1, v2, which is 1, 0, and then 1, 2. So 1, 0, 1, 2 does form a basis for R2, but it's not the standard basis. And excuse me. So we have a point 3, 2, but 3, 2 is in this new basis here. It's not in this. We want to see what would this be like in the standard basis. So this why is, because the standard basis is, now we're calling it B prime. What, you know, that's B and that's B prime, and that's U1, U2, and U1 is 1, 0, 0, 1, and U2 is 0, 1. As I said, this is often called I vector, and it's often called the J vector. You know, it just doesn't matter. It's just what it's often called. Anyway, so what does it mean xb equals 3, 2? That means that the vector x is equal to 3 times v1 plus 2 times v2. But v1 is 1, 0, and v2 is 1, 2. Now, if you multiply this all out and add it up and distribute everything that you wind up getting 5, 4. Now, 5, 4 is 5 times the I vector plus 4 times the J vector, and therefore the coordinate matrix of x relative to this new basis, of course the new basis is the standard basis, will be 5, 4. And here's a picture of it. So here we have, this is v1. So v1 is 1, 0. v2 is 1, 2. And if I take 3 of these guys and 2 of those guys, I wind up getting up here to the point that we know and love. I'm sorry, to 3, 2. Now we don't know this point is 3, 2. We know this point by a different name. We know it is 5, 4. But if you're using this basis, it's it's 3 guys this way and 2 guys that way. And you see how the picture is all slanty, and it kind of represents that. In the bases that we all know, where it knows have little rectangles here, so it's 5 of these horizontal vectors and 4 of these vertical vectors. U1 is a 1-inch, you know, that's 1, 0. U2 is 0, 1. So 5 of these and 4 of those, and we get to that point. But it's hard to say. It's almost like an optical delusion. But this vector here and this vector there are the same vector. They're the same length and the same angle, or I should say the same magnitude and the same angle and the same direction. And so this is really just 2 different ways of saying, of describing or the same vector. That's really what this is. It's just 2 different ways of saying the same thing. Let's look at another example here. We want to find in example 3, we're kind of doing the opposite. We're doing what we did in example 2, but it's kind of the opposite direction. In other words, in example 2, we got coordinates in terms of a non-standard basis, and we convert it to a standard basis. Now we're given the coordinates in the standard basis 1, 2, comma -1, and we want to find what would be the coordinates of this vector in terms of this non-standard basis 101, comma 0, -1, 2, comma 2, 3, -5. Now, before we're going to do this problem, but before we do it, I just want to remark that technically, you see, you shouldn't really trust anybody. You know, a great mathematician said that. Said if you want to be a good mathematician, he used to tell the students, if you want to be a good mathematician, then you should believe everything I tell you. And if you want to be a great mathematician, don't believe anything I tell you. Meaning figure it out for yourself. So really, what we should do is make sure that these three vectors really do form a basis. And for R3, which means we should really show that they span R3, or show that they're linearly independent, or something like that. If there's R3 we know is 3 dimensions. So if I have 3 vectors, I just got to show that they're linearly independent, or show that they span. If you want to show they're linearly independent, one way to do it is to stack the 3 vectors up into a 3x3 matrix, and then see if that matrix is invertible or not. And you could either do Gauss-Jordan, whatever, to put into reduced row echelon form. You could take the determinant to see if it's non-zero. There's a whole bunch of ways you can show that 3 vectors are linearly independent, and that's technically something we should do, because we're just telling you it's a basis, but you should really check out for yourself that it's a basis. Anyway, let's go and do the problem now. So we begin by writing X as a linear combination of these 3 vectors here. So 1, 2, -1 is going to be some constant, some scalar times 101, plus plus another scalar times 0, -1, 2, and so on and so forth. And now what we want to do is, if I would multiply this out, I would get C1 times 1. That would be in the first component. C2 times 0 will be inside the second component. C3 times 2 will be inside the third. Oh, sorry. This is the first component of the first vector. This is the first component of the second vector. And C3 times 2 is the first component of the last vector. Well, I'm adding these all up. And when I add them all up, they should equal the first component of this guy, which is 1. So that's why we get this first equation, C1 plus nothing plus 2C3 is equal to 1. And then we do the same thing for the middle components, and then for the last components. And that's why I get these 3 equations. Now, what I want to do is, instead of writing this system of equations this way, I want to write it as a matrix multiplication. AX equals B, where A is my coordinate matrix, X is the variables. So I'm looking. It's interesting how these scalar constants are now being viewed as variables, and this is the B vector, which is the constant vector of the constants. Anyway, we would solve this somehow, and I do have another video where I show you how to actually solve this step by step. But basically, if you would solve this, you would wind up getting C1 equals 5, C2 equals -8, and C3 equals -2. So our original vector X, X being 1, 2, -1, is equal to 5 times 101 plus -8 times 0, -1, 2, plus -2 times 2, 3, -5. Let's just look at the first position and see how that works. We get 5 times 1 plus 0 minus 4. So we get 5 minus 4, which is 1, and that's exactly what it's supposed to be. It's supposed to be 1. We'll just do the second one. I'm not going to do all 3. Let's just do the second one. Here we get 0. Here we get +8. And here we get -6. 8 minus 6 is 2, and that's my 2 right there. That's my middle 2 right there. And there you go. We've done exactly what we wanted to do. Now, what we just did in the previous couple of examples was we did a change of base. It was what they call a change of basis, meaning we had components in the standard basis and we changed them to the to equivalent components from a non-standard basis. Then we did. We also had one where we had components in a non-standard basis, relative to a non-standard basis, and we changed them to components relative to the standard basis. We don't actually have to have the standard basis be all. We could have given a set of components relative to one basis, and then go and change them to components of that same vector relative to a different basis. I mean, one non-standard basis, then change it to a different non-standard basis. We don't, we have to give two examples with both of which involve the standard basis, but we don't need that at all. But let's just look at what we did. We had this, here's C1, C2, C3 were the components of the vector X relative to the basis B prime, which happened to be in our example non-standard. And this 1, 2, -1 was the components of X relative to the basis B. It happens to be, in that example, B was the standard basis. And we basically multiplied this vector by a matrix, and that matrix is called a transition matrix from B prime to B. Why? Because I have a vector that's written with coordinates relative to B prime. I'm multiplying that vector times this transition matrix, and the result is a vector relative to basis B. So this matrix over here, which I'm calling P, is a transition matrix from B prime to B. It turns this B prime thing into a B thing. That's exactly what's going on here. And so that's how we do a change of basis from B prime to B. Oops. Now, to perform a basis from B to B prime, well, what I'm going to do is I'm going to multiply both sides. By the way, that's the matrix. This is another way of writing it. That's the matrix P, multiplying it times this vector X relative to B prime, and the result is the same vector X, but now it's relative to B. Well, I could multiply both sides of this equation here by P inverse. So this becomes just plain vector X relative to B prime. This becomes P inverse times vector X relative to B. And this now is a change of basis from B to B prime, because I have the basis, I have the vector according to B. I multiply it by this inverse matrix, and I get the same vector, but now written as in terms of its components relative to B prime. And that's the transition. So the change of basis that we did in example 3, that was just the last example we did, that can be represented by matrix equation that's C1, C2, C3, because that's what we were trying to do at that time. I took 1, 2, -1. That's what I was given. See, don't forget, in the example that we did, example 3, we were given the 1, 2, -1, and we needed to solve for the 5, -8, -2. So basically, if you multiply that times this, now where did we get this vector from? This here is the inverse vector of that guy up there. And again, in one of my other videos, I made a bunch of short little videos, and I show you step by step how to get the. But that's just finding an inverse matrix, which is something we were trained how to do. Anyways. So this is the coordinates of X relative to B prime. This is the transition matrix from B to B prime, and that's the coordinate matrix of X relative to B. And that, my friends, is the story. And here's a theorem, theorem 4.20, the inverse of a transition matrix. If P is the transition matrix from a basis B prime to a basis B in Rn, then P is invertible, and the transition matrix from B to B prime is given by P inverse. and that makes again makes a lot of sense. Here's a lemma. Now, what is a lemma, by the way? A lemma is just a theorem, but it's a theorem which I guess is used primarily to prove a different theorem. So, so in other words, before you could prove the 4.20, which is the theorem I just showed you a minute ago, you need this thing right here. So if B is the basis for these vectors, B prime is the basis for those vectors. These do not necessarily have to be what's the word I'm looking for? Standard bases, whatever. They could both be non-standard, doesn't matter. So if I could express V1, V2, Vn, if I could express the B vectors in terms of the U vectors, because each V vector is a linear combination of the various U vectors, well, these scalars here are going to form the transition matrix. But notice it's not in the same order. Notice that here it's C11, C12, C1n, which is what you have here in the column, C11, C12, C1n. So this Q is actually sort of the transition matrix of the coordinate matrix of these coordinates. And we use that to solve 420. And this leads us to another very, very important theorem, which is that if B is a set of vectors and B prime is a different set of vectors, each of which is a basis for Rn, then the transition matrix from B prime to B, P inverse from B prime to B can be found using Gauss-Jordan elimination on the n by 2n matrix. That's when you have these like double side-by-side matrices. B prime comma B as follows. You attach the two matrices, B prime here on the left, B on the right, and then you do your Gauss-Jordan elimination until the left side looks like the identity matrix. So what's on the right side is going to wind up being P inverse. And again, this is a little different. This is similar. Reminds me of finding an inverse matrix, and we are finding an inverse matrix, but with a little twist. And again, I worked out examples. We're going to see examples in this video. Plus, I worked out examples in other videos of how this works, what to do, and how this works, and so on and so forth. Alrighty. Let's actually do this. So let's look at example 4. We want to find the transition matrix from B to B prime. So what is B? So B in example 4 is the standard, as you can see, it's the standard basis of R3. B prime is a non-standard basis of R3. By the way, B prime is the same non-standard basis that we saw in example 3. Anyway, so first we use the vectors of the two bases to form a matrix. All right, so we take the standard vectors and we line them up. We take the B prime of basis vectors here, line them up. Notice that here they're horizontal, we make each one vertical, but that's how we do it. Now I take B prime and B and I put them together in that order. So B prime, which is this guy here, goes on the left, and B, which is that guy there, goes on the right. I do a whole bunch of Gauss-Jordan elimination until I have an identity matrix over here. And whatever you have on the left side, on the right side, I mean, that is your P inverse. And I'm just going to write it individually. This here, which I just copied these numbers, is P inverse. So if we multiply, which means if we multiply P inverse times the coordinate matrix 1, 2, -1, then we get the result is going to be the same result that we got when we did example 3, which is going to be like, what was it, 582 or 5-8 -2 or something like that. What was it in example 3? I think it was 5 -8 -2. Okay, let's go back to that spot. I just want to point out one more thing. Here we go, example 4. So let's do B2, B prime. So there you go. Anyway, this 1, 2, -1 is in the standard, that's our B. So if we take P inverse and multiply this by P inverse, we get the 5, -8, -2, which was relative, it was the basis B prime. So it all works out and it's all good. Yay for us. In the last problem, we found the transition matrix from one basis to another basis, but one of those bases was the standard basis. Here we have an example, example 5. We're going from one basis to another basis, but neither basis is the standard basis. B is this guy here, -3, 2, and 4, -2. And B prime is -1, 2, and 2, -2. And it's easy to see that these are linearly independent, both of these. So first we make the matrix, we want to go from B to B prime. So we put the B prime here and the B over there. And so we write it out like this. We want to turn this into the identity matrix and just let the other guys just follow along for the ride. And when we do that, and you could figure out the steps on your own, when we do that, you're going to get 1, 0, 0, 1 over here on the left side, and you're going to get -1, 2, -2, 3 on the right side. So this here is going to be your P inverse. This is going to be your P inverse, and it's going to help you. And when you multiply B times P inverse, then you're going to get B prime. So now, if we were looking for, if in example 5, we wanted to go the other direction, then I would have put the -3, 4 on the left side, which is what I have right here, and I put the -1, 2 on the right side. Then I do my evil and my damage, and I get this right here: 3, -2, 2, -1, and that would be the transition from B prime to B. Yay! I'm calling that P. And to verify that it's the inverse matrix, you can either, now how do you verify a matrix is an inverse? Either I could take either one of these matrices, do our process to find the inverse, or I can just multiply these two matrices and see that I get the identity. Those are my two. Well, that's it for 4.7. Next time we meet, we'll be in 4.8.